Okay. So today we were the first one will be seeing how the data visualization is being done and how it is useful to analyze the data properly. If you are not familiar to Python, that's fine. Just see, it will be interesting because we are having this type of plots that you are seeing here. So it will be interesting to see what is going on here. And if you are familiar to Python also, that's also good. I will provide you the code if you are interested to have them. I'll give you the program files and you can practice them at a later time. So data visualization, actually what is this? So we can have different amount of data or quantity of data, and our data may contain various number of rows and various number of columns. So if the data set is so vast that we need to present in a certain way so that we will be able to see what is going on in that data set and how the data is actually distributed. So after learning the data, it will be easier for any data scientist or any researcher, whoever is doing any sort of analysis using this data science or data mining. So it will be helpful to them. After they learn the data or analyze the data, they will be able to select any algorithm. You have seen many sort of algorithm like support vector machines, other sort of classification algorithms where we want to make some sort of prediction. So to do that, you need to first study the data set, how it is distributed. So this program or the code is basically concerned with the data visualization only. So first we need some of the libraries to be imported. These are some of the libraries. We need NumPy, Pandas, Matplotlib, and Seaborn. So because we are going to apply some sort of functions which are being defined in all these libraries, that is why we are just importing them. And here see we need the plots in the format of in this way. There should be two rows. First one is a scatter plot where the data, the first point, it is somewhere here. Your Let's take this one. Okay, this point. So it's at 0 and somewhere in between the -1 -2, correct? So these different dots are nothing but the points or the values defined in your data set, and this type of plot is called as your scatter plot. So here from this you can see that some of the data points are closely defined, okay, or present in the data set, while some of them are mm, distributed with certain gap or having space in between them. So from this it will be really helpful to do the classification by application of some sort of algorithm. Then histogram, if you want to display your data in the format of this type of shape, okay, this will give you how the data is distributed starting with somewhere, let's say -3 here, okay. So -3 up to somewhat exceeding after 2. This type of structure is called histogram. This is your bar chart or bar graph. And time series means if the data is displayed in this way. So if we have in the x-axis, we have the dates. You can see there are different dates starting with January 1st, 2018, and some values in the y-axis. So this type of data is called time series. And box plot, that is, if you remember in the beginning chapters, we have a data visualization technique called box plot. So there are different segments in the box plot. You can refer to that slide in the first two chapters, and you can see how the median value, the starting value, ending value, what does it mean? What does the box plot represent actually? So this type of box plot is also doable through our Python libraries in data mining. So let's see how we can write the code to have this type of structure, this type of plot here. So first, what we need to do, we have to set up a box to have multiple plots, 3, 4, 5, 5 plots in this way. So the whole figure size will be 8 by 5, the length and breadth. Then we are having for 5 plots, we are having 5 axes, x1, x2, x3, x4, x5. And for their positions, for their positions, we have some sort of setup made here. So 0001. So this actually define the position of all the plots in this whole big plot. We just defined their positions. Now the thing is that how to create each one of the plots. So let's first see the scatter plot. So scatter plot, for the x-axis, you see here we have certain values. In y-axis we have certain values. So we need those values. After we get those values, we can just use to plot them. So from the NumPy library, we are calling the linspace function. So there is a function which will create some sort of random data within a range. And that random data range is in this way, minus 0.75 to 1 with a gap of 100. Okay, so this actually creates some sort of data for the x-axis. In the same way, using another one random function, the y-axis values are created. So after you have all the x-axis, y-axis points, to have all the points like this, so here each point in the scatter plot is a combination of the x-axis value and the y-axis value. Okay, so how to now plot it? Just use which plot is it referring to, which axis, ax1. So ax1 dot scatter, use the x-axis y-axis value, and it will just simply plot it in this way. So the outputs are actually shown here. Okay, so after you run the code, you will see this type of scatter plot is plotted. You just take the x-axis y-axis values and plot them using a simple scatter function. Nothing else is needed. Okay, so this type of plot is actually possible through the import of the matplotlib library, and you have used the numpy library as well. Because of that, we have imported them in the first segment. Then let's see how the histogram is formed. So first, just create the x-axis values. So the histograms, we need to have the x-axis values first. And again, to that, we are just adding some random numbers into it, and using that x-axis values, it will just plot the values in the format of a histogram. This structure is called histogram. And okay, so okay, I missed this set title method. So set title actually sets the title of which type of plot is it. So from here you can see this is a scatter plot, this is a histogram, this is a bar chart. Likewise, let's come and see the bar chart. In the same way, the x-axis y-axis values are defined. After you have them, just use the bar function, and ax3 is for the third plot, right? So ax3 bar function will use the x-axis values, and we want to properly align them. The alignment may be skewed a little bit. So to avoid that, we are just using this parameter setting the width, and another parameter for something. It has to do with the shape of how the bar chart is formed. Just remember that you don't have to go get into details of that. Then from here we can see that the x value for, let's say this is your 2 3 4 5. Okay, for 5 the quantity is actually high by looking at this bar, and for the x value 1, the distribution is very less. Here the distribution of the data is very high, and here it is very less. So using this analysis, you can then proceed ahead what is supposed to be done later. Then now let's see the time series and the box plot. In the same way, as in the time series you have dates, we need to create some sort of x-axis values with the dates like this. Okay, So starting with this range and periods as 100, we are taking, uh, okay. So we are just creating a date, all the date values in the and storing them in the XY variables here and trying to just plot them. So it will have all the values in this way. The y-axis values are distributed from -2 to your 4. So this is how the time series plot is formed. And there is another one thing, set title. I just told you to set up the title. The SetXSticks. Whenever you have to plot this type of time series data, you need to do some sort of arrangement to your dates, or otherwise they don't be visible in this proper way. Okay. So xsticks, you have, if you have taken Python, you could remember we have a slicing option where you can perform this type of slicing using these two operators. So we want the dates in the gap of 30 days. Okay. So see here, the first date 1 1, then after 30 days it's 01/31, then March 2nd. So this is the pattern in which we want to put up our set ticks. So these are nothing but the x-axis ticks. So that is why it is called set x ticks. Okay. Next, lastly, the box plot. Just create some random values for the x-axis values, and just box plot function will make this box plot in this way, and this gives you some meaning of the data distribution. Okay. I hope you find this interesting to look at. And don't worry, there will be no assignment from this programming, any sort of programming related to it. Um, and if you are not familiar to Python also, don't get into details of how we have the syntaxes or what is functions on some other syntaxes or concepts. Just see what we are going through, and I hope you find this class interesting. Then we have used matplotlib. Now we will see how using Seaborn, this library, there are certain functions how you can perform, you can do your own plots. Okay, so this is a Seaborn plot. If you see, this is one segment, this is one histogram, blue part. Let me tell you. So actually there is a, let me annotate it. There is a data set which is called iris data set. It's a flower data set actually, and it's freely available. If you also want to practice something, you can, I'll tell you how to import this. You can also import this type of data set freely available in anywhere. You can just search it and you will find this data set. This iris data set has 3 different types of flowers: Setosa, Virginica, and your versicolor. Yeah, versicolor. We are not doing anything with the versicolor for now. We are just dealing with our Setosa and Virginica. So blue part here is showing actually what is this, what data it is taking. In the data set, there are 3 flowers, 3 classes. Okay, and they, each of them have their own characteristics. That is what is the petal width, petal length, sepal width, sepal length. If you have taken botany, okay, botany, if you remember some of the flower species, okay, they have petal, sepal, all those terms. So looking at their size of the sepal, petal, their width, height, we define which flower is it, whether it is Setosa, Virginica or versicolor. Okay, just for now, make a picture that what we are trying to achieve here. It's just a flower data set, and we are trying to just distinguish them from each other. So Setosa flower is actually given by this histogram. This is how the data is distributed. The density is given in the y-axis. And in the x-axis, actually, we have the sepal length. Okay. So sepal length for the, what it means actually, what does it, does this plot means? So yellow color is your Virginica, blue color is your Setosa. In the x-axis, we have sepal length. So if you see the top first part here for 5, so for 5 sepal length, your density is actually high. It's exceeding 1.4. Okay. And here, somewhere the sepal length for in between 6 to 7, 6 point something, the Virginica sepal length is high. So here you can see that the sepal length is actually based on the distribution of data set. The Setosa sepal length is actually higher than your Virginica. This is some sort of conclusion we found from the data set. Now let's see how to form this type of plot. Okay, so see here, as I told you, you need to first load the data set. Okay, to load the data set, let me tell you this. So from Seaborn, we are using this library with a temporary name as SNS. And now we will use that SSN temporary name to load the dataset. When you use the load dataset function iris, it will directly, it's already there in the Python library, it's associated. So it will be directly downloaded and it will be stored in DF. So what is this DF? This is your pandas. Okay, pandas. We are using pandas. This pandas actually store the data in the form of tables. Let me do one thing. Let me run the code. It may take some time. Just give me a moment. Okay, it's done now. Let me do something. Okay, I'll add it here. We will first load the data set. It's loaded. Now suppose after the data set is loaded, we want to suppose see the data set. Can you see this? This is nothing but a data frame. So there are different species, okay? Setosa, Virginica, versicolor. Okay, there are dots means actually there are 150 number of rows and 5 columns are there. As I told you, these are the different characteristics and their values. Okay, and DF means this is shown in the format of a data frame or a table. Now we are going to do our plot using all these values. Now, next what we are doing in the Setosa and Virginica variable, we are trying to filter out the species Setosa with the sepal length values, not anything else. Okay, that is stored in Setosa. And Virginica, we are doing the same thing. Just filter out the data frame or the table based on the species Virginica only and its associated sepal length. Okay. So after we got this, let's set up the figure size. What will be the whole figure size? Length and width, sorry, 7.6. And I'm on parameter to make the image proper, the plot proper. Then in the Seaborn library, we have distribution plot. For Setosa, it first will show the blue colored part. Then for Virginica, it will have the Virginica part in the plot. Okay. And this is the format how it will be provided. And this is how the distribution is. From this line also, you will see that how the data is distributed. Then you can set up the title. The legend is actually whatever data, two types of classes are there, right? We have just Setosa and Virginica, correct? So as we just have them, you can just plot them here in the legend, and show means the plot will be displayed to you. Okay. So these are some interesting examples of data visualization. Do you have any question in this? Okay. So yeah, that's good then. Give me one moment. Um, so let's just start up with this one. So if you remember the support vector machine we studied earlier, So support, we are going to apply the support vector machine algorithm into a given data set, and we will see how the data will be classified, being separated or yeah, distinguished from each other. So to do that, these are some of the parameters we are setting up and also importing the libraries. Then we are actually using, I have used the iris data set. Okay, load iris will just load the data into iris data variable. And there is a make moons data set as well. From the sklearn data sets library, you can just import the make moons, and make moons function will randomly create the data set with the x and y training set variables, x moon, y moon values. So this is actually a two-dimensional points. That is why this is for x dimension, this is for y dimension. So first, let's see how the data set is actually distributed. It looks complex, okay, but just to we want to learn how the different sets or types of data in the iris and moons data set, how they are distributed. So let me just tell you what is going on here in the plot. First, we need to set up the figure size. Okay, so 18:6. So in the whole figure, so this is one plot. This is one plot. So these are nothing but the subplots. Subplot. They are called subplot. So first subplot. So to set up the parameter 1 to 1, 1 to 2. So first 1 to 1 will correspond to iris, and this one will correspond to 1 to 2. Then next we want to plot for the iris dataset, right? So as I already told you, iris dataset has 3 flower names. Okay. So when you have the data, that is, it will just take the columns, first 2 columns of the given data set. Target is 0. Here target is 0 means it will correspond to a particular species. It may be Setosa, may be versicolor, may be virginica, the way in which it is declared in the data set. There is something automatically it's done. Then these are some of the formatting that we apply. Okay, apply so that the points will be displayed in this way. So how we are having 3 different points? Because we are plotting 3 sets of data categorized in this way. Setosa, versicolor, virginica. Okay. When you plot this, the Setosa flower, so this is a section where the data is distributed in this way. They are more closely placed to each other. Versicolor, virginica, they are closely placed to each other. Okay. So as we are having different, we are having different colors. So these colors are these markers, YO, BO, RO. Due to that, we are having different colors. So this is the distribution. Then for X label, Y level, title, legend. So for X axis, this title, we are adding this petal length. So actually, these are the features. They are considered feature, and in the dataset it's already defined like that. So that is why we are just having feature names and their corresponding index. So then we define the y-axis name. Then for legend, so we use this legend location upper left. We need it in the upper left position. That is why, and the font size is 14. So this is how it will display the output. In the same way, for the moon's dataset, we are just going to do the same thing. The moon dataset has 2 classes. Okay. So for the 2 classes, if we write this type of 2 functions, see how the data is distributed. Class 1, the blue one, and red one is your class 2. Okay, then we set up the x-axis, y-axis title, then the legend in this way. So next, if you remember the support vector machine, in the support vector machine, the support vectors or the hyperplanes are most important, right? So there are, because of those hyperplanes, we can segregate or distribute our data in 2 different ways. Either we can have a hard margin. Hard margin means what? In this properly hard way there, that means this is your major hyperplane, right? The two boundaries, the decision boundaries they are called, if you remember. So in the decision boundary there are only, here for the blue versicolor there is one data point, and for setosa there is one data point, and there are no data points in between this your margin. Okay, so whenever we want a hard margin, that means it's actually distributed or differentiated in a proper way. Correctly we can say that there is a gap, that means these are two different categories. Okay, there are no data points in between both of the margins or two of the two decision boundaries. So how to get the decision boundary or the hard margin in this way? Let's see. So if you remember, um, so first here we need to get the exact x iris, y iris, the data and the target part. Let's not go into detail of that. So here actually what we are doing, we are just considering the petal attributes. We are mostly emphasizing on petal attributes, not the sepal attributes. And to get a binary value, we are having these three lines here. Then the next, see how can you get the boundaries. Here you need to apply the support vector machine. So actually in sklearn library, we have SBM. Okay, so from SBM we can import the SBC function, and if you remember, we have linear kernel, polynomial kernel, Gaussian distribution kernel. So we are, for hard margin we are just using linear kernel. This is a setting. You will just write the parameter and it will do everything automatically. Then some extra parameter which are also needed with that, and then your model is fitted with those two binary data from the x iris, y iris. So after it's done, the model is fitted. Next thing is that you need to create the boundaries, these two boundaries, right? So these two boundaries, for to get them, there are two basic things: the coefficient and the intercept. So you will just use the model that is being fitted, its name and the coefficient. Uh, you can call it a parameter, not a function, it's a parameter. Okay, W is your coefficient and B is your intercept. Okay, so why again we need them? Because if you remember this equation, do you remember Wx, Wx2, Wx1 plus Wx2 plus B equals to 0? Okay, so if something is in the middle, this is the equation. And for getting some points, uh, so if you have the boundary like this, right? So this is your margin, this is your, oh sorry, what am I doing? And this is your margin, correct? So some points, this may be your positive side, this may be your negative side. So for the middle part, this is your equation, Wx plus b equals to 0. For the positive part, you can write Wx, if there is only one point, b greater than 0. And for this one, you can write W, hope you remember this from the SVM, Wx plus b less than 0. We are just applying that same equation. So from this, we get a decision boundary. So after getting the decision boundary, what we will have from the decision boundary, the formula is 2 divided by your coefficient. Okay, so from that we get the margin, and there are two different formulas: gutter up, gutter down. What is this? This is your gutter up, this is your gutter down, to have the decision boundary in having with some specific values. And after defining the gutter up, gutter down, it is actually needed for your strict decision boundary for your linear SVM hard margin. Then if you want to see what are the support vectors, okay, what are the support vectors? If you are asked, This is your given data set. What are the support vectors for the classification? You can just simply use like this. Have your model, then implement support vectors, support underscore vectors underscore. And now it will, SVS will print all the support vectors for it with the values. Now using all the parameters that we just derived from the previous program, what you can do, you can define the figure, then plot CLF, another one function which is needed for it. Then we want the actually the points in the format of a scatter plot. So that is why we are having this scatter plot function in this way. Okay, then they using those decision boundary, gutter up, gutter down, all those things, and the plot functions x level, y level, legend. We have now the classification in between the setosa and versicolor only. And remember, this is only based on the petal characteristics, not the sepal. If you want, you can also refer the data set and see what are the sepals, and based on the sepal width and length, you can see how the data is distributed, in which way. Then this is your hard margin, then soft margin. So what is this soft margin? Let me, rather than going through the code, I'm showing you here. We are just basically repeating the same thing. There is a little bit difference. Here, see, we have a case 1 and case 2 here, right? So if you see the width is much larger here rather than this one, okay, the second one. And if you see the difference in between the hard margin and the soft margin, there are some of the points lying in between the hyperplanes. That is why we call it soft margin. So these are actually basically overlapping with each other, which makes it difficult to classify them. Okay. So in this case, so if we have this type of situation, so how these margins are different from each other, this code is actually doing that. The margin is too small over here, and there are less points in between the hyperplanes or the decision boundaries. So if the data is distributed in this way, actually versicolor and virginica, after applying soft margin, it is also difficult to distinguish, make some distinguishing between them, right? So how to properly classify them? What is the solution here? So solution is here nonlinear transformation, the kernel based SVM. So nonlinear, if you remember, there are some kernel functions in the slide while I was showing you. There are some kernel functions we use, the polynomial kernel, radial basis function kernel. Okay, so we are going to use those, and after applying those, see how the data will be distributed in this way. Correct. So this is one case here, a polynomial kernel. So for this, okay, so here first we need to import the SVM. We need to first import the data set, right? After you get the data set, the first part is doing that. You need to create the model, fit the model with the data, and while defining the SVC function, you need to define which type of kernel do you want. Okay, and some other parameters as well, and these also make difference to your various models. So the first one, if you see this one, its own parameters and the polynomial kernel is classifying in this way, but the RBF kernel is classifying in some different way. See how it is distributed. So like this, we actually define 4 different types of models: SVM, CLF1, CLF2, CLF3, CLF4. Correct? Uh, Now we, for prediction, we write some extra lines. So actually these are basically what they are doing. We are reshaping our data. It is in a given in a defined format We just want to reshape it. After you reshape it, for prediction purpose of data, we need to define the decision boundary, right? And something it has to also do with the creation of the support vectors as well. So this part is achieving that. After you have everything, you can just use the plot code here that is being defined. As I told you already, so these are four plots. So for this, we have four sections: first plot, second plot, third plot, fourth plot. And here there are different functions. These are some of the functions which are used for plots, setting up their labels, x-axis, y-axis, their title, legend, all those uh, characteristics, whichever is needed. So these are some of the kernels, and with the assignment of different types of parameters, how the distribution is actually done. So you can look at this picture and you can tell me which one looks efficient to you. Okay. So this one is more accurate if you see here, you know. So you have to do, if you are doing this type of coding or doing the support vector machine classification, you will apply different parameters. I mean, if you don't know anything about the data set you want to classify, you will see that still using this setup, there are two blue points which are getting overlapped with the red points. So how will you classify the blue points, whether it is versicolor or virginica, right? So it will be difficult to achieve that from the data set. Here also same thing happening. Some of the red points are inside this blue part, but this one you got an optimal solution. You may call it optimal solution, okay? Because applying this, it is being the data points are distributed in a proper way. You may use, there are other uh, kernels also, and using other different types of parameters kernel. There are so many parameters or kernels. I am just showing you four here. You will just apply all of them and do the analysis in your own way to reach to a particular optimal solution, based on your requirement. So this was performed on the iris dataset. In the same way, on the moon dataset, this type of kernel setup is also performed. Okay, so see how with polynomial, with Gaussian, with polynomial and some other setup we can see here. Yeah, so this polynomial kernel has degree 3, coefficient 1 and c value as 0.1, but here this polynomial has c value as 100, and that's what is making that difference in both of them. This polynomial, there is just a difference of c parameter value 0.1 and 100, and see how it is defining the boundaries. Okay, still you are using the same polynomial kernel but getting different results. Same thing also happening in case of Gaussian as well. The RBF kernel, radial basis function. Okay. So is there any question? I understand most of you are not familiar to the Python programming. Okay. But still I just wanted to show you how whatever you are learning, how they are applied practically. So I'm going to stop the recording.